the bell for more thought-provoking content.
Modern physics has two distinct areas. There's the standard model, which includes quantum physics, and there's general relativity. The standard model describes physics in smaller and smaller terms, and sometimes even in the smallest terms. It gets all the way down to subatomic particles and quantum mechanics. General relativity, meanwhile, looks at the largest things in the universe. Things like gravity, stars, black holes, and galaxies, and how they all function. These two models don't outright contradict each other, but they don't yet exist harmoniously either. And so, ever since Einstein published his theory of general relativity, scientists have been trying to unify these two models into a theory of everything. In late 2022, a study published in Nature and looking at theoretical wormholes may have unlocked a theory of everything contender. Specifically, the scientists working on it, many of whom are based at the California Institute of Technology, Caltech, and/or Harvard University, may have found a theory of quantum gravity. Traditionally, gravity is the key concept that has defied efforts to translate it into quantum terms, and is the main block in the theory of everything search. But here, the problem may be solved. At the heart of the study were computer simulations of wormholes, built to show how these theoretical structures might actually work. Broadly, a wormhole is a bridge in space-time, where reality bends so much that vast distances could be crossed by passing through one. They're a staple of science fiction, and as weird as they are, they absolutely could exist as long as Einstein's theory of general relativity is correct. In the real physical world or universe, we haven't found any wormholes yet, but that could be for a range of reasons. Wormholes might be extremely rare, for example, or nearly impossible to detect, or they might be very short-lived, meaning that even if we did detect one, it would be long gone before we could ever hope to reach it. The earliest models of wormholes that we do have suggested that they would at least be very unstable and liable to collapse if anyone or thing were to somehow try to traverse one. But there are other solutions to Einstein's equations that produce different types of wormholes for us to consider. Scientists also speculate that micro-wormholes could exist. These would be tiny, but far more stable than a large and typical wormhole. The potential for these has been made clear thanks to the 2022 study, during which the wormhole sims were created through a quantum processor. Without an actual wormhole nearby to study, this is the best option we currently have to get a hands-on look at how they might work. And it's something we've only been able to do recently thanks to the advent of quantum computing. Today's processors can transfer information at subatomic sizes through quantum bits, which, rather than be either a 1 or 0 permanently, like they are in standard computing, are both a 1 and a 0 at the same time until they are observed, existing in a quantum superposition. This is certainly complex, but it has before been aligned with the famous Schrödinger's cat thought experiment. As Schrödinger's cat can be simultaneously alive and dead until it is observed, quantum bits, or qubits, can be two things at once. For our needs today in this experiment and in others like it, this means they can store far more data far more efficiently than a regular computer ever could, and therefore that they're capable of creating such deeply complex simulations about gravity and cosmic phenomena, including about wormholes. By getting into the real details of wormhole physics using quantum computing, this study has been able to provide an early description of sorts of quantum gravity, with apparent demonstrations of quantum information being passed through the simulated wormholes. There's one more key concept to add into the mix, though: quantum entanglement. The team behind the study were initially investigating how the concept of quantum entanglement can relate to wormholes. In quantum entanglement, particles are inherently connected to one another no matter how far apart they are, creating an instantaneous link between any 2 points. Not only is quantum entanglement important for developing things like faster-than-light communication systems then, which could lead to instant communication between Earth and other planets, but it could be a route to teleportation. Teleportation, as it usually appears in science fiction, may seem instantaneous on Earth, but it's actually limited by light speed, just like other forms of communication and data transfer are. But not so with quantum entanglement. If we have two entangled particles, one on Earth and one on, for example, Pluto, we really might be able to send information between here and there instantly. But again, back to the theory of everything quantum gravity study. The scientists here have looked at wormholes through this lens of quantum entanglement, using the principles of entanglement to study how a wormhole can exist in two places at once while still being connected. Once more, it all mostly checks out via the quantum computer sims. The study is theoretical science in practice to a point. So really, there is a lot going on here. Not only has this study presented possible descriptions of quantum gravity, thereby potentially edging us closer to a theory of everything, but it could also help us to soon develop fantastical technologies like teleportation, quantum communication, and a tangible means to physically travel faster than the speed of light. Crucially, though, this study isn't yet a home run. It doesn't actually provide a theory of everything, more a route towards one. And ultimately, it's going to be a while until we can push it further, because quantum computing is really the bleeding edge of current technology. We are still at the first iterations for so many quantum procedures, so there's a lot still to come. In this field, maybe more than any other, scientists are waiting for technology to catch up with their ambitions, to turn wormhole sims into something even less video game and even more real. But finally, what happens if or when a true theory of everything is ever confirmed? With it, we'd be able to understand the universe like never before. We'd be able to describe extremely complex objects and events that have previously escaped our full understanding. It would revolutionize physics and science as a whole, perhaps even more than Einstein himself did when he published his ideas in the early 20th century. With a theory of everything guiding our greatest minds, there could soon be no mystery unsolved, no physical problem left standing. And of course, it's not as though this wormhole experiment is our only hope. There are other, sometimes even stranger, theories and experiments in motion that might also one day break the laws of physics as we currently understand them. Something like string theory, which reimagines all the particles of the universe as one-dimensional strings that interact with each other and vibrate in different ways, might yet provide the answer. String theory has a long list of high-profile supporters, too, though it also has the unfortunate problem of requiring many additional dimensions in order to work. Many more planes of reality beyond the 4 that humans are able to perceive. Nevertheless, string theory, and its even more complex sibling M theory, have been a part of many major developments in mathematics and physics in recent times, which, if nothing else, shows that we don't need an absolutely perfect and correct theory for it to still be useful. Perhaps with this particular wormhole study, then, it won't lead to a cohesive theory of everything either, and we'll have to take another route to reach that endpoint. But that doesn't mean it can't still teach us plenty about how wormholes might function in the wider universe. For many, this is certainly something we need to explore more, both from the perspective of how wormholes work and from the point of view of improving and creating truly useful applications for quantum computing. When it comes to space exploration, there's one view that sees human beings of the future jetting through the cosmos, planet hopping, and galaxy cruising. But there's another that sees a much more efficient and less risky approach involving complex AI geared toward digital, quantum, cosmological modeling. It's what this study is an early version of. And that's how scientists really might have discovered a theory of everything.